Hi, this is Chaitanya and I'm going to give my presentation on energy efficiency and the storage flexibility in the blue file system. The authors are Edmund B. Nightingale and Jason Flynn. Coming to the authors, uh, Nightingale is presently working for Microsoft, and his research interests include operating systems, networks and communications, and hardware architecture. You can clearly see the graph of his publications and citations. And Jason Flynn is working for University of Michigan. He is basically the academic advisor for Edmund, and well, he do have 82 publications, and these two guys are doing a good amount of academic research for Microsoft. Coming to our presentation, this is what roughly my presentation is going to cover. Coming to the introduction. Yeah, as discussed in the paper, we are presently in pervasive computing. This can also be termed as ubiquitous computing, where personal and shared data can be accessed anywhere, any point at any point of time. Also, there is a very fundamental vision developing towards this computing because we are continuously followed by the wireless networks and the sort of stuff. But the only limiting factor for this mobile computing is that the battery life is limited for mobile computers or mobile devices like laptops, handheld devices, and hard disk won't suffice computing when you want to perform mobile computing. Why? Because hard disk account for considerable amount of energy consumptions in mobile computers and the laptops, right? So efforts have been done to save disk energy, but they are only limited it's to mechanics. Why? Because definitely rotational disk platters, the main mechanism for the disk is to work done by rotating the platters. Definitely there will be seek time, rotational latencies time, and sort of stuff. So you can get a clear idea when you see the slide. Basically, hard disk has three cycles. Generally it would be any of the three states, like standby state, active state, or idle state. So the graph over here, initially, for example, consider that the hard disk is in the standby state, and when a new request is received, like this one, new request is received, the disk, basically two types of operations will be performed. The disk is either spin up or the spin down. What is the spin up means? The disk is transmitted from the standby state to the active state whenever it receives a request. So upon serving the request, the disk will definitely be set for sometimes for idle. And what the latest research done is, if the disk is idle for a specific period, for specific, the timeout will be some specific timeout threshold will be there. To save the energy, the disk is spun down, right? So that after, for a couple of seconds, you can see you can observe over here, the disk is idle for example 20 seconds. This is a timeout threshold, and the disk is spin down. Nothing but this disk is again transmitted to the standby state, right? In this way, this is very efficient, right? We are saving the energy. But what happens when in a couple of seconds again a request 2 is done? Then the disk has to automatically spin up, right? Again it has to be taken to transmitted to the active state. So as you can observe that this spinning up and down disk raises substantial energy and time overhead. So hard disk are not at all a good option for mobile computing. Then comes to flash drive. Definitely flash drive are a good option. They're low energy devices and they're very portable. We can carry gigabytes or even terabytes of data simply on the road. But this is not also a solution for the mobile computers. Why? Because the problem with the mobile computers or mobile computing is the limited battery lifetime of mobile computers, right? It's not the mechanics of the storage devices. It's the problem with the battery lifetime of the mobile computers. So we need a new mobile system, new mobile file system, which should be energy efficient. So as discussed in the paper, the motivation is that we have lots of networks and different sets of bandwidth, but every time it's a power hungry networks, and the storage devices, as we now clearly saw in the previous slides, how the disk transmission of disk from one mode to another mode is consuming lots of energy. So they definitely tax high the limited battery capacity of mobile computers. And as much more of storage devices are there, we are going to have a lot number of replicas of objects across computers and their portable storage devices. We have iCloud sort of stuff also. So there is a danger of viewing stale data and inconsistent updates. And mobile data access performance is definitely a function of storage access times. We know that every storage device has its own mechanics of accessing the data. So there should be some sort of dynamic power management when we are accounting for heterogeneous storage devices, right? So the final problem definition is the storage is evolving rapidly, right? A specific time period, we are seeing a lots number of evolutions in terms of device mechanics, right? The memories, I mean, to the cost of the storage is substantially decreasing, and maintaining a terabytes of data is a very simple issue. We have lot like this, the micro SDs, flash drives, mobile things, everything. So it's keeping much efforts on changing the mechanics of the storage devices won't just increase the power, decrease the power consumption rates or sort of stuff. The research should be done on mobile file systems to adaptively decide when and where to access data based upon the performance and energy characteristics of each available device. So definitely there is a need for energy efficient file system. So though much of the related work is done, these are all the distributed file systems, and upon all these, the CODA and look-aside caching are the best file systems, I can quote it. And CODA works similar to BlueFS, but the only difference is that CODA is not at all an energy efficient file system, and it's only static. It just follows a static hierarchy of integrating portable storage devices. We can later see about these things in comparison with the BlueFS and the experimental results proposed solution. So here the authors proposed a new distributed energy efficient file system, BlueFS, keeping in emphasizing much on two concepts. The first one is adaptive cache hierarchy to reduce energy usage and efficiently integrate portable storage, and reduces client energy usage by dynamically monitoring device power states and fetching data from the device that will use the least energy. So the first goal is change is constant. We already discussed that, right? New types of storage devices are being deployed, and each storage device has its own mechanics of accessing data, whether like flash has some sort of different mechanics, and battery backup DRAM has different mechanics of accessing, and they do different accesses times also. And definitely we clearly seen from the previous slides that how the power management, the transmission, we check the disk power mode transmissions. So obviously performance is a has definitely impact on the power management. And networks vary, right? Each network has different bandwidth, and each storage device has different dimensions, so access times vary across storage devices. So what the authors trying to inculcate in BlueFS is that they are trying to provide BlueFS with the adaptive cache hierarchy, where to monitor adaptively or flexibly monitor the performance of each local, portable, and remote storage option available to them a mobile computer. And I think it's a dynamic adaptability or dynamic integration of different portable storage devices, right? And the next one is power to the people. As we discussed in the barriers like that, there was heavy use of power storage and network devices by distributed file systems, which in turn are giving much more high cost for pervasive data accessing, right? And as we discussed, not much of the effort or research is done to make these file systems very energy efficient, right? So the strategy is that basically the data means we have two operations, read or write operations, and they emphasized more on considering the energy cost for read operations, where they can reduce the consumption of energy, and aggregating write operations, and integration with the device power management strategies. You can take with you the third goal, isn't it? So definitely the BlueFS has to leverage the benefits of the portable storage, but portable storage is not a mobile data panacea. Why? Because the particular portable device can be lost, stolen, or damaged. Sharing is hard, and replications will lead to inconsistent or stale data. So the BlueFS integrates portable storage into file system. So this is what overview of how the BlueFS works. Initially you can see that the data is copied to all the storage devices, one to the BlueFS server. This is the hard disk and this is the flash memory, and we can simply carry the portable storage to home, and we can access. This is how the BlueFS works, right? So, and this is the underlying implementation of the architecture. You can see from over here that basically it works simple to the previous slide, but it consists of some technical terms, like you can see there is a kernel module, applications. We know that the applications for files which need to access the data or sort of stuff, and VSF operations, and Linux file cache. Basically the BlueFS system is implemented on a Linux file system, so that Linux file systems cache, and lots of the different variety of storage devices like this, and Wolverine and a BlueFS server, right? So now what actually is a kernel module is, the BlueFS contains a kernel module, and it's a very minimal, that is a thin kernel module, that is it doesn't contain much of the functionality. In other words, it's a very simple, fairly standard, and it only contains replicas of the data and some operating system functionality. Other than that, the functionality of the BlueFS kernel module is very thin. It just intercepts the VS of operations. Actually, what actually is a VFS is, it's virtual file system operations, nothing but these virtual file systems let the client applications to work very freely on any sort of concrete file system. They allow the client applications to work freely on any concrete file system. So whenever application issues an VSF operation, that VFS operation is simply the whenever a VSF operation is issued to the kernel module, this kernel module simply sends an upcall. Upcall is, as we discussed in previous papers, right? An upcall is sent to the Wolverine. So Wolverine is here. This is the main important part in BlueFS architecture, where the system does, it's a user level daemon, right? Much of the functionality, client functionality, is carried out in Wolverine. So these are synchronously directed to the Wolverine, where the Wolverine resolves that request, and upon once the request is resolved, the copies are sent to all the storage devices and to the BlueFS server also, right? So as I said, the kernel module different consistent semantics by redirecting operations that modify data, such as write, create, and rename to daemon. And the main functionality is, for example, checking for serializability, or lazy writing, or and the operational log sort of stuff. So the functionality is very thin, and we can check what lazy writing is actually in the next slides, right? So coming to the Wolverine user level daemon, as I said, this is a very important component in a BlueFS architecture. Initially, Wolverine issues for each local portable and network storage device a write queue is attached, and already a write queue will be there for the server also. Why only the choose and write queues is, the other side, the write queues can improve asynchronous writing. They can focus on much on the asynchronous writing, thereby which performance can be improved, and aggregate writes can be performed. As it's a data structure, we can aggregate all the operations, and we can just push it like that. And serializability, so the queue generally, the basic dimension is the FIFO, first in first out. So however, in whichever order the modifications are done, in the same order the modifications are reflected back to the server. So in that way we, in that way we can eliminate inconsistencies. And how actually this works is, Wolverine issues a hash table for every queue and for every objects in that queue modified by the queued operations. So whichever objects are modified by the queue operations, that thing is reflected back to the hash table. By making use of this, the modified operations can be tracted. And as we saw on the previous slide, BlueFS main emphasis on lazy writing, nothing but write back delay. So it just won't push each operation one by one. So as we have seen in the disk that every time, if to save the energy, the disk will be automatically set to standby mode, and to transmit from standby mode to active mode, that's going to take much of the energy. So to reduce those power mode transitions and minimize the energy in such power mode transmissions, rather than flushing one operation one after the another, write operations are performed in aggregated way. A bunch of batch jobs are submitted, like batch of write operations are submitted to the server. So in that way, so generally this approach follows a default of 30 seconds timeout. After 30 seconds, default is 30 seconds, but it can be changed. The 30 seconds after timeout, the write operations in the queue will be flushed to the server. And that flushing can be done by making use of a command line tool. Not much of the information is given regarding how this command line tool works like that. And the next one is the bursted device patterns. As I said, you can clearly get an idea. See, for example, consider this as some sort of queue. See, this has openings, right? Whenever a VS of operation is performed, the thing for each device that's stored in its own write queue. And see here, every operation, consider this as an object, right? So every object has a number on this, that this object is nothing but the reference count, how many times the object is referenced, that can be counted on that, right? So this is done because to conserve the memory, objects can be shared among the right queues, and based on the reference count, they are flushed or updated or modified to the server, right? When I click on that, so first in first or right, so one operation is done, after that one is completed, the next, this is similar to bursty device patterns, nothing but when one operation is flushed from the queue, the remaining all operations in queue are flushed at a time. Because as I said, the thing is we need to save the energy, right? So all the operations are just flushed one at a time. So whenever one operation is flushed, one object is flushed from the write queue to the either micro drive, either portable storage, or to the BlueFS server, the remaining all operations are flushed. To write to many next is this. So aggregate writes a batch of jobs, and write to many. And write to many basically is that each portable storage device has its own storage access time, right? Most of the time the access times are very high for disk. So that so to the, for that reason, multiple replicas of objects are stored in multiple portable storage devices, and this can be counted for if one fails we can get from the another, and also if the device with the least power consumption can be picked up when we need particular data, right? In that way also Wolverine follows approach of writing to many, to all the portable devices, storage devices. Next, read from many. So read operations, actually there are no sort of locking mechanisms to perform read or write operations in the BlueFS. The only thing is when we have a bunch of portable storage devices, so the BlueFS monitors cost of reading data, nothing but for every reading data the cost is estimated. What actually the cost covers is the access time from the storage and the device power mode transitions for each device. So these are kept aside whenever a particular read operation is done, and whichever device gives the best performance. Giving the device the best performance is nothing but how much is its predicted latency and how much is its energy uses. These two factors are considered, and whichever gives the least energy consumption, or whichever has the least energy consumption, that device is best picked to get the data from that device. What is eNote cache? So till now we have seen that initially we have seen whenever a particular data is to be read from portable storage devices, BlueFS checks all the things, right? The Wolverine checks all the portable storage devices, and it gets the estimates, right? If the data we are being read is not in particular storage device, then it's really a waste of time and effort, energy, right? So we have thing is the system should be energy efficient. So for that, the authors get this idea like eNode. eNode is nothing but an in-memory index. Whichever the currently access to objects are there, they are being indexed with the eNode. It's a memory index. So basic idea is to minimize the fruitless loops, right? So how this works is basically every object is hashed with a file ID, and these all the recently accessed objects are all hashed with the file IDs, and these IDs are all stored in the eNode cache, some sort of buffer like that. And the eNode bit, the index stored is a bit, it's a sort of a flag bit like valid or invalid. If that particular object is present, what the user is searching for, client is searching for, is present in that particular device, then the objects are validated and checked for reading the data. If that object is not present, then that device is skipped, we go for the next storage device. So in that way, eNote caches minimizes the fruitless reads. And coming to storage devices, the basic FSL style device interface approach is the same for all the storage devices. And the reward devices communicates basically using TCP based RPC package, and LRU style caching of objects. Why? Because we're accessing multiple couple of variety of portable storage devices, and we need to keep only the least recently used objects. So that was done. And the cache of here, it's very portable, nothing but we can retrieve BlueFS files and also non-BlueFS files. That's the portability provided by the cache. And as I said, not all blocks in the file are to be cached. So whichever objects are termed to be valid, those are the things. So every file contains whether the object is valid, partially valid, or not. Based on that valid bit, that blocks are cached in the are cached. And for to remove the inconsistencies, each cache is updated with the latest version of data being read by the user. And next important, very interesting concept is affinity. Till now we have seen that the cache just holds only the working set, right? Working set of objects that are needed by the user at that time, and they can be flushed when the application changes, or when we to move to new process, or the when client changes, right? But definitely is a something interesting concept where the user would prefer to always have a certain set of files on a particular device. He can keep them permanently and they can't be evicted, right? So for that concept is called as infinite. Whichever files or whichever group of files that the user wants to keep, those files are being set with an affinity bit. So a command line tool is provided for the users to add, display, remove affinity for files and subtrees. As I said, if the affinity bit is set for a particular file, then that object, particular file, object, or whatever, the object is never evicted. So fault tolerance, obviously, so we are working in a distributed environment, so fault tolerance is we have emphasized. So as the thing is, every write or modification is authenticated by server. I said now BlueFS identifies every object with a 96-bit identifier, and every object has its flash hash file ID, and whenever a read or write operation is to be performed, that hash ID is checked to check whether that particular object is valid or invalid. So only upon that authentication only that modification is done to the server. In that way we can tolerate errors. And the time delay to flushing all the write operations to the server is 30 seconds, and they said that 30 seconds worth crash updates are only will be erased, and I don't guess 30 seconds is worth or not. And BlueFS server, it's fairly standard implementations. We said it's very, and the only difference with remaining file systems is that the remaining file systems are not energy efficient. And when it comes to BlueFS, it is energy efficient, and it's aware of individual storage devices, atomicity, durability, nothing but atomicity, the serializability order, and the sort of stuff. And cache consistent is the most important work. Cache consistent is something that we can, as I said, the BlueFS didn't have particular lock setting mechanism when it is performing read or write operations. Multiple reads can be done without any damage, but what happens when concurrent writes are performed, and which one should be updated, and what happens if consistency arises? For that, BlueFS generally follows two approaches: optimistic replica control, this is inherited from CODA, and callbacks for cache coherence. What actually happens is, as I said, every object has its unique identifier, and also every object has a version number associated with it, right? So whenever a particular object is being written by user, we also checked with the reference count number in the earlier slides. So when the reference count is automatically incremented, and if a particular data is modified and it is ready to be written to the server simply checks in the cache the version number, and if that version number is only one bit higher, one time higher than its earlier version, then the server feels that it is consistent, and it simply writes it. Or else sorry, or else it takes as some issue, and it asks for the manual what you can say, manual resolution. We can see in here, right? So we do have copies in the hard disk and the flash drive and the server also. So automatically whenever the operations, we just by making use of this device, we just perform some operations on a home system, and that modifications are updated to the flight server, which in turn is updated to the remaining devices, right? Adding and removing storage devices, as I said, it's very simple. Whenever a portable device is to be attached, first we'll check with the detachment. In that way we can get to know some technical terms. A detached message is sent to the server, and new operations are not placed on the device write queue, and retrieves and stores the current version of the objects. Operations remaining on the write queues are flushed, and server's write queue is also flushed. Enode cache is written to the device, and a clean shutdown record is written to that device. And when a portable device is attached, checks for the clean shutdown record. The Wolverine checks for the clean shutdown record, and if it is fine, then it sends an attached message to the server, and the if, invalidated objects, if invalidation is nothing but if you're not able to find objects, but if we want to find the objects in all the portable storage devices, but as we are making the device newly attached to the definitely the objects will be invalidated. Such invalidated objects are deleted, and inode cache is formed. The particular set of files which user is interested in that device is made to be set in the inode cache, and any refetch requests are there, they are rescheduled. And this power management, this is nothing but integrating with different portable devices, and making device management very dynamic. So for this, they adopted a technique from one of the previous researchers, that is nothing but self-tuning power management, where by making use of this, a BlueFS system can get information about all the power management strategies of all the devices it is connected to with, and even it will be able to know the device transitions, nothing but the power modes transitions from active to standby or standby to idle, like that sort of stuff. Sorry, idle to standby, like that, able to think. This is the thing. But if it is case with one access at a time, what the final the only thing the finally others consider it as a hindrance is, if you are going to perform if you are going to access data from the disk, if that data is a large amount of thing, then transiting from standby state to active state would definitely somehow benefit. But if you are accessing, if you are just getting only one block of data, then transmitting from standby mode to active mode is not at all good, and the benefit is also the much of the power energy is consumed for that sort. And for that, they just included another functionality called the ghost hints. The idea is very, the functionality is simply clear. So obviously, when the disk is not in the active state, it will be in the standby state, where to save the energy. If you want to read a particular large file block of data from the devices, so disk spinning up disk and spinning down, as we know, it's very costly. So what they're issuing is that they are going to issue some ghost hints. Hints is nothing but some sort of issue command, like that. So ghost hints to the device. Initially they will get the data from the network. Initially, the accessing the data from the accessing the data is channelized to the network, where blocks of data is being read from the network server. For each block that is being read, a ghost hint is issued to the disk. So whenever a hint is issued, the disk incrementally raises from the sleep, and try to transmit to the active state. So the disk is in that process of spinning up. In the meanwhile, we can read the blocks of data from the network server. Once the disk spins up, the remaining blocks of data can be read from the disk. So in that way we can say the time is also being saved, and the same way we can say that we are reducing the consumption of energy by the hard disk, right? Next, so evaluation goals. The only thing is, they want to evaluate the BlueFS with the other distributed file systems, in terms of portable storage, in terms of reduction of the client energy usage, in terms of the heterogeneous storage, and in terms of how adaptive cache hierarchy provides benefit to the BlueFS, right? So the first one is masking the latency of power management. As we said in the previous slides, that uh, the disk is definitely in the standby mode to save the energy. When the disk is in the standby mode, we need to read various files, right? So BlueFS is that it picks the files from the server until the disk spins up, and once the disk is spinned up, it reads the files from the disk. So this is the thing. But when it comes to the conventional, all the older file systems, they have to wait a time of 800 microseconds to let the disk spin up, then only the data is accessed from the disk. When it comes to BlueFS, it's not the case. So BlueFS reads, they took some 4K files up to 60 times faster than EX2. EX2 is a different distributed file systems. It's not an energy efficient. And support for portable storage. uh, so actually, they did here evaluation on three file systems: Coda, Lucasite, and BlueFS. They're in a file system trace. A trace is nothing but it's a collection of some system operations. It's a, like we can say, it's not clearly a benchmark, but it contains a file consisting of system operations, and this file is run on different portable storages. And as you can see, that WFS is 44% faster than Lucasite, up to 3 times faster for high latency. And energy efficiency, as Purcell is a trace program we discussed with the trace, right? And they took one Purcell a trace file, and they just only ran 10,000 operations, keeping in view the time for the methodology, and they make use of only half full cache. This is also called warm cache. Nothing but only half of the files, currently accessed files, are kept in that the cache is only filled half, and with the currently accessed files, right? So we can clearly observe that the blue stands for BlueFS, and another one is the coda. And interactive delay by 76%, and it consumes 55% less energy than coda. Heterogeneous sources means when multiple heterogeneous storage is, or the heterogeneous storages are what you can say upgraded to somewhat level, how they checked with how BlueFS performed, and they ran the trace program with the full cache, and you can say that the interactive delay is reduced by 45%, and BlueFS consumed only 25% energy, right? And coming to of all the experimental results and evaluations, we have clearly seen that BlueFS clearly reduced the client energy usage, and it integrated portable storage by making dynamic power management and dynamic dimensions also, various access delays inherent to pervasive computing. And the future work they just is to include much of the caching policies and elimination of double buffering. The double buffering is something which we encounter in the BlueFS server when we are going for the lazy writing. To account for the lazy writing, to nothing but to work for the write back delay, a dirty block is used. A dirty block is used to keep track of the pages that has to be returned back, that are last modified, and that has to be returned back to the server, where they make use of the double buffering approach, and this is somewhat overhead on the server. So and their future work included to eliminate the double buffering, and by increasing much of the functionality of the kernel. Thank you.